Computer programs generally use many variables stored in the register and memory. Because they are faster, we want to store the variables in the registers to execute the program quickly. To do so, the compiler optimized the code in such a way that it uses the least amount of registers. However, for many programs, the number of variables used is much more than the number of available registers. This is true even for seemingly simple programs. Imagine a function that calculates the average of elements in an array. It might seem like it only has 3 variables: the array itself, a loop counter, and a variable to store the sum. However, the compiler might introduce temporary variables for intermediate calculations. If the array is large and the compiler introduces several temporary variables, the function might exceed the available registers. In such cases, when we do not have enough registers, we can use the stack for storing data. Register spilling refers to a situation in computer architecture and compiler design where the number of variables used in a program exceeds the available physical registers in the processor. When this occurs, the compiler needs to store some variables in memory temporarily because there are not enough registers to hold all the variables at once. This process of moving variables from registers to memory is known as register spilling. Register spilling can have a negative impact on program performance because accessing data from memory is slower than accessing data from registers. Therefore, minimizing register spilling is important for optimizing program execution speed. In computer architecture, a register window and register spilling are closely related concepts that deal with optimizing the use of registers within a CPU. In a computer architecture without register windows, when a function is called, the CPU saves the current state of its registers before jumping to the function code. The CPU then jumps to the entry point of the function code to begin executing it. When the function finishes executing and returns, the CPU restores the previous state of the registers from the stack or memory. This process of saving and restoring register state incurs overhead in terms of memory accesses and instruction execution, particularly for programs with many function calls and returns. Register windows aim to reduce this overhead by managing the register state more efficiently. The register window concept is commonly found in architectures like Spark. A multiple register window is a technique used in computer architecture and compilers to efficiently manage the usage of registers in a processor. It involves having multiple sets of registers available, typically organized into windows. Each window represents a distinct set of registers that can be used by a process or a function. The window is divided into 3 fixed size areas. Parameter registers hold parameters passed down from the procedure that called the current procedure, and hold results to be passed back up. Local registers are used for local variables, as assigned by the compiler. Temporary registers are used to exchange parameters and results with the next lower level, procedure called by current procedure. The temporary registers at one level are physically the same as the parameter registers at the next lower level. This overlap permits parameters to be passed without the actual movement of data. Keep in mind that, except for the overlap, the registers at 2 different levels are physically distinct. Thus, the actual organization of the register file is as a circular buffer of overlapping windows. At any time, only one window of registers is visible and is addressable as if it were the only set of registers. The next window becomes visible only when required. The latest version of Spark typically have 8 or more windows. So, even if there are multiple function calls, a new window can be assigned for the new function call. This mechanism allows the processor to quickly switch between different sets of registers without needing to access memory, thereby reducing the overhead associated with register spills and improving performance. Register windows offer significant advantages in scenarios where reducing function call overhead, improving register management, and optimizing performance are critical factors. As a result, architectures with register windows, such as Spark, are often well suited for server environments, high-performance computing systems, and other compute-intensive applications where maximizing throughput and minimizing latency are priorities. While register windows offer these advantages for servers and high-performance computing, they may not be as critical for typical desktop or consumer-oriented applications, where factors like energy efficiency, cost-effectiveness, and compatibility with existing software may take precedence. Computer architectures without register windows typically employ various techniques at the compiler level to minimize register spilling and optimize register usage. By employing these techniques, architectures without register windows can effectively manage register usage, minimize register spills, and optimize performance across a wide range of software applications. Thank you for watching the video. I hope you learned something today. Have a beautiful day, and see you in the next video.